Welcome to machine learning and material sciences. So today we are going to cover. Okay, yeah. So I believe we are all working on our projects, and then this is one thing that keeps on coming. So I thought I would spend one class on this one, and then there can be one more class on something, and then we can attack one more problem statement for materials. So today we want to understand what is class imbalance, let's say, and like what can we do to basically solve this particular problem. And you will understand why this is very important because this impacts model performance as well. Doesn't matter how good of a model you have, if you have this problem, you will end up with bad results. And we will look at some of the methods that have been in use for a very long time, as well as some of the new methods I will just speak about. Uh, and there exist, and libraries do exist for all of them. And sometimes you have to write on your own, but I will showcase a few on how to do so. Fine. So we'll just start with the class imbalance problem. So today we'll be tackling one of the most common, but yet challenging problems in real world machine learning. Right? So class imbalance, and if I would have asked questions to probably everyone in working in machine learning, let's say, when they look at the real data, and I ask the question that have you worked with imbalanced data sets? Almost all of them probably will say yes. Yeah? And in your field also, like in material sciences, there will be something that will be looking for, it will be having class imbalance, right? And we'll just look at a few of them. So, yeah, sorry. So here, for example, real world examples, for example, fraud detection. So you can understand, for example, UPI transactions takes place in India, almost every transaction is now, let's say, UPI, small to big. And if you look at that entire transaction history, you will find out 99.9% of them are legitimate, right? So there will be only few percentage, like 0.1% or so, fraudulent transactions. And similarly, medical diagnosis, if you take a look, like majority of this blood test and everything else that we do, most of them will come out maybe like negative. Negative as in they are good tests when you are healthy, but there might be 1 to 5% chance of actually detecting some anomaly in your blood report. And similarly, manufacturing defects, now though it has been clearly improved, so but you can still get very minor defects. And then spam detection, if you look at it, most of the emails that come are generally okay, but there's still a huge number, like 20% spam. And then anomaly detection, right? So anomaly detection is a very general term, but it applies to everything else also. But if you see that anomaly is an anomaly because it does not occur often, right? So 0.1% are only anomalies and 99.9% are normal behavior, right? So then what's the problem that we have? Uh, so all our standard machine learning algorithms, they're basically designed to give you, let's say, higher accuracy, let's say, or the idea is basically if they start with the assumption that the number of classes are balanced. Right? So classes here, hope you understand, like fraudulent or legitimate, disease or negative, defective or normal, spam versus non-spam. Okay? So now and because we assume that there is a balanced class distribution, and if we optimize for overall accuracy, then of course things are okay. But what happens when 99.9% of your data is just one class, right? So then if I just predict all of the emails to be, let's say, non-spam, let's say they are legitimate emails, or let's say fraud detection, I don't care about fraudulent because I just care about accuracy, so I'll just declare every email as legitimate. I will not overcut all. Then I will have 99.9 accuracy percent accuracy, but then I have learned nothing, right? So basically I will not be able to detect fraudulent transactions at all. So So we have to understand here. So that means there is a real world problems are generally imbalanced in number of classes, and the algorithm assumes something, but the reality is different. And this is definitely very important when the stakes are very high, right? For example, fraudulent transactions, spam or defective, manufacturing defects, these are all very high stakes. Like if you miss those, something bad will happen in cascading manner. Yeah? So now the next thing will be like few questions you could ask, like when does imbalance become an imbalance? Is it 70%, 80%, 20%? At what point does it become imbalance? The answer is basically there is no such, how do I say, hard margin for all those things. But if you generally see like 10 is to 1, like 10% to 90% distribution, if that is there, then it will start causing problems with our general ML pipeline. Yeah. So, okay. And uh, anything that will be like 1% or let's say 99%, if you have such kind of scenarios, of course, like we will have to have the same machine learning algorithms looking at it differently, right? So I just wanted to point out that this particular exercise or this particular lecture is identified for that case. Like, what if there is a class imbalance and you're trying to train the best ML models, you're not getting good accuracy? So this is one of the problems that could happen in your case. And so if it does happen, then what do you do? Yeah. So I think this is just like a more explanatory example. So let's say imagine you're building like a fraud detection system, right? So you have 10,000 transactions, 100 are fraudulent, and 9,900 of them are legitimate, right? Uh, Now, what is the easiest model to build? Basically, predict everything as legitimate, right? So there is no code even required, there is no training required, just predict everything as legitimate. We have accuracy of 99%, right? But then this particular predictor was supposed to find out everything fraud, right? So then this does not work at all. Now, entire business has failed. Now, basically, all your spam emails, or let's say all the fraud transactions are going through, then the entire financial system fails. Now, if we just look at the math, it's like a very standard, how do I say? Give me a minute. And let's say just before we go to there, just training data is like D. I have observation xi, I have a label yi, I have imbalance ratio, that is the number of majority by number of minority. There are other places where imbalance ratio is the other way around, like the number of examples in minority classes divided by number of examples in the majority classes. So just take care, matlab, as in even if it goes other way around, just make sure the definition is consistent. And anything with rho greater than equal to 1, all the standard loss functions will start to fail. Yeah. Now standard cross entropy loss looks like this, and with if we have an imbalance of, let's say, uh, sorry, yeah, if we have an imbalance of, let's say, 100 to 9,900, then majority class will contribute to basically 99 times of the gradient updates, right? And model will eventually start learning not to do anything when it's sees minority. Yeah? And the decision boundary will be basically towards the majority classes. And all the optimization techniques that we have studied, gradient descent or otherwise, and loss functions, they will all make it move towards the majority class. Just declare everything as majority, even if you train. Yes. So then, okay. So now, how do we solve this? Right? That would be a question. Uh, any So one of the ways to solve this is like, for example, let's say we can tell, okay, so anything that is fraudulent, let's assign it more weight, right? So that means finding one fraudulent weight correct will be 100 times more than finding one decent email correct. Yeah. That is definitely an approach. We will cover this in this slide. So now, before jumping into like what are the methods and what do we have, So we will just go ahead and first look at the metrics that we use to judge an imbalanced data set. So the idea is to, like, we need to measure it properly before even jumping how to fix it. So accuracy is definitely not a nice method. We have seen already. And then, so then what we use? So before we go, what do we use? There is one simple thing called confusion matrix. It's basically a like a 2x2 matrix, but like each row and column has different meanings. So there is actual positive, actual negative, and predicted positive and predicted negative, right? So if we assign columns and rows accordingly, then what we have is true positive. That means we predicted positive and the answer is actually positive. Now, true negative, we predicted negative and it is actually negative, right? And then false positive, we predicted positive but actually negative. False negative is we predicted negative but it was actually positive. Yes. So with this, we will basically derive the things that are important to us, right? So one of those matrices are here. So these are precision and recall. Precision basically tells of all the predicted positives, how often are we correct, right? So precision is equal to true positive by true positive plus false positive. And the goal is this. Basically, whatever we are predicting, are our positive predictions reliable? That means if we predict something to be positive, let's say, if we label an observation to be positive, then are they reliable, right? Otherwise, if we predicted too many false positives, then this precision value would be very low, right? Because it is TP by TP by plus FP. So that means we have to be really, FP has to be really close to 0 for this value to be close to 1, which is what we want. And so one of the example is, like, for example, few false alarms, right? So for example, let's say if somebody does not have a disease, we should not claim it has a disease, like that's a false positive. Yes. Otherwise, there will be just random number of medicines that you will take for a medicine which for a disease which did not have, which you did not have. Now the next is recall, otherwise known as sensitivity. It just says that, so the first one was of all the predicted positives, how many were correct, or our predictions, if we predict positive, are they reliable? Other way around. Recall says how many of positives did we find? Because the precision, what we can do is precision can only predict uh, like very conservatively work also, right? It will not try to find out or do anything more. Sorry. Now recall says, like, of all the positives that are there, how many did we find, right? So it's true positive by true positive plus false negative. So it's basically asking, did we find all the positives or no? Fine. So high recall meaning we did not miss. Basically, if we had high recall in, for example, spam detection, then we are basically detecting every email that was supposed to be spam, we detected it. Now, if you look at these two, precision and recall, there is a trade-off. You can get 100% recall by predicting everything as positive. Hmm. But precision will be terrible, right? You can get high precision by predicting positive only when you are absolutely sure, right? So that we don't make any false positives. But then we will miss many cases because we are not taking chances on something that could have been true positive as well. Only when we are truly sure, only we can do. So what we understand is basically precision and recall will be, there will be a trade-off. You can never have good precision. I'm not saying you can never have, that is the goal, but there is a trade-off involved. So, and okay, fine. So now what we do, so we have precision and recall, then because they have a trade-off, what we use is F1 score. So F1 score is basically an harmonic mean between precision and recall. It balances both the concern. That means I need to have high precision, I need to have high recall. How do we do that? Right. So yeah, and then we have also like F1 F beta score, weighted harmonic mean, and 1 plus beta square. precision into recall by beta square into precision plus recall. All it says is basically if you have beta greater than 1, it's basically you favor recall. That means don't miss any diseases. And if you have like for example beta less than 1, then you make sure that you don't filter important emails. That means good emails should not go into spam, right? So this is one of the very nice metrics, F1 score. If you look at any of the papers that you are studying right now, they generally will have this like F1 score reported if it is like an imbalanced data set. And the next metric that we have is Matthew's correlation coefficient. It ranges from -1 to 1, and it works very well also with highly imbalanced data set. Note down the formula, I hope. So the key points here are basically accuracy is definitely not working. Precision versus recall fundamental trade-off is fundamental. So what do we use? MCC is there, and F1 score is there. F1 score, although it's a little bit more widely used than MCC, but maybe it's a better metric for our projects. And you can always, whenever you are exploring or trying to understand, medical diagnosis and spam detection is something that you can always think about and have this in your mind if you don't understand recall and precision well, right? And then, for example, one question for your exam could be like, why did we use harmonic mean and not, let's say, just arithmetic mean? Yeah. But anyway, that is a question for you. This is like a homework question. Now the next is there are two more of a visual input. You can call it as a metric, but it's more of a visual input. We do calculate AUC ROC, but ROC curve itself is basically like a visual understanding of uh, during class imbalance, how are we doing? So, ROC is basically receiver operating characteristic. It was used all the time, so that's why the name. But otherwise, it plots between true positive rate, that is recall, versus the false positive rate. Um, and as we vary the threshold, it keeps on changing, and then it's a x and y axis, and then it's a curve. What we do is we find the area under the curve, right? And a perfect classifier will have the area to be equal to 1. And but there is a minor issue with the ROC for imbalance, not minor issue, but majorly it can be a little bit more optimistic than we require. So the reason is because the false positive rate that we have, it uses two negatives in the denominator, right? So, and when you have too many true negatives, like in an imbalanced rate, the false positive rate will remain low, right? Even if we have too many false positives, let's say, we have actually captured, let's say, have false positives, but if the true negatives, if we have a lot of true negatives, then also it will make it artificially low, right? So there is a minor issue. So the other way around to use it, it's called a precision recall curve. It's the same thing. It's basically x-axis will be recall, y-axis will be precision, and then we'll draw an area under the PR curve. Yes. So for imbalanced data sets, the PR curve will be a little bit more informative than the ROC curves, and you will find both of them everywhere. Maybe ROC is a little bit more popular in case you, but I think time you can make it more popular, the PR curves. So PR curves will be relatively more, how do I say, better for determining the performance on the minority classes. Okay. Now what do we do? Right. So we studied. So just to give a repeat, we studied class imbalance problem. We understand what was the problem, why there is a problem, and then what are the metrics for evaluating if there is a class imbalance or not. Fine. Now, how do we solve this? Uh, the solution is basically two ways. So one, you can attack it from the data level, and the other way around is basically you can attack it from the algorithm level. Hmm. Uh, so yeah, and it can be from the algorithm level. The simplest approaches will be like, for example, oversampling what we have. So assume you have like majority classes, let's say 90 of them, and then 10 of from minority. You can just uh, uh, randomly oversample on the class samples. So what will happen is you just duplicate the minority samples or observations that you have, and it's like pros are basically it's simple. There is no information loss. Cons is basically we are just creating exact duplicates. So if the machine gets trained on those exact values again and again, because in a single epoch we are still looking at the observations again and again because of the duplicates that we created. No new information comes, and eventually we overfit. Now the other way we can do is random undersampling. So undersampling would be like if we have again majority, we'll just instead of selecting all the 90 observations, we can select fewer of them. Hmm. Now pros are of course like the same way like it will faster training of course and balanced classes we'll get definitely because faster training because the number of data set reduces the size. And cons are, of course, like you will have information loss. It will basically, whatever information we had in majority, that information is lost and the data set size is reduced. And typically in all our fields, we require like the data set to be very varied and all this, even if they belong to like the majority class. Right. So now random oversampling, random undersampling, they have some advantages, but eventually there are cons are bigger. So what people do is something called a like a smoot. Yes, smoot is one of the very old algorithms that people started using, but it's still being used because it's very simple also. So, like the clever idea is instead of duplicating, you can just create new synthetic samples, right, of the binary. It's still oversampling technique. So what do? We pick a minority sample, xi, and we find its, let's say, k nearest neighbors, which are the closest, and then pick any of the neighbor randomly among those k nearest neighbors, and then you create a sample in between, like at a point in between the line connecting between the initial minority sample that you picked and the randomly selected neighbor. Right? So if you draw a line, you pick any point at it. So, and here lambda is basically selects at what portion it has to collect, like what point in the line it has to be pick up from, and it is basically a uniform distribution from 0 and 1, the value line. Now, why is it a better technique than duplication? Yes. So typically you are generalizing the minority class distribution because you are trying to fill up the space in between two minority class data samples, right? It is of course interpolation, and this is a very widely used baseline. Almost everybody uses this one, and this does not consider basically any of the majority classes distribution. That can be a worry, and it might also result in generating some samples which are typically should not exist ever in the, let's say, experimental process or otherwise. um, so again, Smoot is still used. Even if it has these issues, it's still used because it works fine and really well. So the next thing is basically advanced sampling. It's an ADASIN. It's a little bit more improved. What it says is that instead of, like instead of generating this minority new samples at approximately everywhere, instead of doing that, you just do it at the decision boundary. That means wherever the line is being drawn between the majority and the minority, let's say, we're doing classification, let's say, you do it there only, closer to the decision boundary. So the decision boundary becomes more and more confident that it's correct or it has to shift. Right? Um, yes, and so now for each, how does this algorithm work? Like you can go through the thing, but very simply, for each minority sample, you count how many of the majority neighbors it has. Then samples surrounded by majority class will get more synthetic neighbors, and basically any of the samples that are very far away, those are called, let's say, safe samples. They will get fewer. Yes. So, and by the way, like you have looked at it, it's basically like an adaptive sampling. Like that means samples that are closer to the decision boundary will have more sampling done, or more samples created. And why do we do this? Because typically it's a decision boundary that is basically struggling to find its place, right? So if we create more and more samples near the decision boundary, it becomes more and more confident. Okay, I'm correct, or wherever I'm moving, that is more correct. So yeah. So again, the idea is. Oh yeah. So there is another one also like borderline smooth. Again, a derivative of the smooth itself. Here, what it does, it classifies each minority sample based on its k nearest neighbor. Then it says, okay, there is a danger zone, safe zone, and noise zone. Danger zone would be like it would be like the borderline samples. So specifically, like half to all members, all of the neighbors will be majority. That's Safe zone will be mostly if you have minority neighbors, then it's a safe zone. Basically, that's where there's no tricky to finding if it is belonging to that class or not. And then noisy zone. Noisy zone is basically completely surrounded by the majority, right? So you're basically picking now for each minority sample, you created minority samples in the k nearest neighbor, and now you're trying to find if classifying those minority samples, right? Safe is everything is within very close. All of them are minority in between k by 2 to k, let's say more than half is basically if they are majority, then it's a danger zone. Noise is basically if it is completely surrounded by the majority class. Now, so it just says that you just apply mode to the danger samples only because noise is anyways tricky. It could be actually a noise. It was supposed to be a majority and just probably labeled as minority. So you just apply mode to the danger places. Yeah. Uh, Now there are few variations of this. Uh, like for example, you can interpolate only between minority samples. Borderline mode 2, for example, you can interpret between minority and nearest majority. Yes. Uh, Advantage, of course, it focuses on augmentation where it matters the most at the decision boundary because that's where those are danger samples are. So now, how the few questions can come like every time you see the mode depends on the KNN, right? So then what should be the value of K? Hmm. Technical, matlab that is it can be diverse as such. K is equal to 5, and around that part is a where is chosen, and it's a hyperparameter, right? So something can perform nice for you on other values. And the next question is like then now that we have SMOT where we could oversample the minority class, where should we should we apply the SMOT before or after the train test split? Right, that would be a question. So generally, the general principle is you only apply SMOT to the training data set. So once the test is split, you only apply SMOT to the training data set. That means the model only needs to see, but the test will be just kept as it is. It will not have any synthetic data points to classify on. Fine. Now that we have covered data related algorithms, so SMOT and variance, we can move to algorithm level variance. And this is one of the things that I think earlier question we discussed. So the idea is to basically, okay, so it's called cost sensitive learning. The core idea is basically make the misclassifying minority class more expensive. Now we what we do, we modify the entire loss function, well, not entire, some part of it, and basically telling that instead of each sample contributing equally to the loss function, now minority samples will contribute more, right? So like if you have more samples, it will be lower weight. Yes. Yeah. So it is basically weighing techniques will be inverse frequency, let's say. So that means more samples, lower weight, fewer samples, higher weight. It's very simple. Yeah? And otherwise, we can have an effective number, which basically says based on diminishing returns, like 100 sample, if you have, like if you are doing it through the way, if the 100 sample will provide you less information than the first sample. Yes. And here technically beta is kept around 0.99 or 9999. And it is more sophisticated, but it is theoretically backed. That means it will give some results, yeah, that are bounded. And then next is square root. Square root is basically like 1 over root over NC, let's say, and gentler weighting rather than inverse frequency. And also it's a little bit less aggressive, like aggressive. So, and generally it might lead to better stable training, right? And of course, like which one to try, I would suggest if things don't work out, you try all of them. These are not very hard. Uh, and then you can tell which one is better. Hmm? And that can basically be your cross validation. Now, focal loss was very popular. Specifically, focal, if you can understand, it's a computer vision related topic. And this was from Facebook, I think, as much as I remember, around 2017. So now what is the problem with that weighted cross entropy, right? So mm the problem major issue was like even if we apply weights, if you see now the easy samples, basically the easy examples, they will still contribute to loss, uh, even in the minority. I told you, like there are safe, danger and noise. Let's say the safe samples will also contribute to your loss where it's not difficult. And yes, and your model will basically start wasting time on those, right? Instead of focusing on the really hard boundary samples. So focal loss comes into picture. It basically says that you downweight the easier samples. Fine. Now focal loss looks like that negative alpha 1 minus pt to the power gamma log pt. Right. Now, if you look at this, the entire trick is basically 1 minus pt to the power gamma. What it says that if pt is equal to 1, let's say, it is confident and very correct prediction that I have. So 1 minus pt will be 0, right? So it's to the power again. So loss itself is 0 because it's an easy. What if pt is 0.5? That means very uncertain. So 1 minus pt again, but it's equal to 0.5, so it becomes like a moderate loss. Now if pt is equal to 0, it is purely confident but definitely wrong. So now 1 minus pt is equal to 1 and it's a full loss. Fine. And gamma also controls how much focus you're doing. That's why it's called focal. Basically, gamma becomes 0, you have standard cross entropy, and gamma is equal to 2. It's a generally people choose that value. It's basically says strong focusing, and gamma is equal to 5. It's like super extreme, and it will ignore all the easy examples. You might not want that. Easy examples still contribute to some part, so you keep some point. And so let me see if there's an example. Yeah. For gamma is equal to 2, you have this pt is equal to 0.9. Let's say easy. Weight factor is 1 minus 0.9 square, 0.01, right? Now easy becomes basically 0.01 value. Now everything that is hard, it becomes 0.25, and if something is really very hard, let's say pt is equal to 0.1, then it becomes 0.81, so it's like, factored in more. So it's a more adaptive way of assigning weights within the minority class itself. Because reweighting just ran equally assigned all the minority classes together, but that's not good enough, let's say, because you want to make sure that wherever you are having confusion, there you have to be more correct. Yeah, it's the same principle as the decision bound, like the smooth borderline smooth, the same principle. Okay. Now focal analysis law, this was, I told you, like it's more of a vision thing. So it was used in object detection, dense prediction tasks, and like highly imbalanced classification. This is a very nice one. And there was also retina net or model, and typically this was used. And so it also looks at in that way, right? So if you know something, for example, if you're studying for an exam and if you know something already, then you don't spend a lot of time on it. Rather, you want to spend time on it which you actually don't know and might be in the exam, right? So that's the point. Now, what are the values of alpha and gamma? Gamma typically 2 and alpha typically, let's say, 0.25. But then you have to do a hyperparameter tuning using grid search. Fine. And then next comes the ensemble methods. These are typically what we do is basically more of a combining multiple models. For imbalanced data sets, we have special ensemble techniques. So one of them is regular random forest will you already uses bootstrap sampling, but then balanced random forest will just help it become better understanding that there is a minority present. Now, bootstrap minority class completely uh, like you bootstrap just the minority class completely. That means you have to include them every time so that they don't go away because each of the observations are important. Then randomly sample or randomly undersample the majority classes only to match the minority class. So if you have 90 and then 10, let's say 75 and 25. So you 25 of minority has to be in the bag, let's say, and then you randomly undersample the majority class. Let's say another 25 you bring from the majority even across all the 75. So in this way, it's basically you start repeating for all the trees. In this way, basically each tree sees balanced data eventually. Like you 25 minority, 25 majority, but you are training across multiple sets of trees. So your entire random forest as a model has seen all of them. Yes. It's a very nice algorithm. And then there is easy ensemble. Okay, so just to go, it's very simple but super effective, balanced random forest. And then you create multiple balanced subsets and you train separate classifier on each of them. And then you combine predictions via voting. Fine. Uh, this one will be like easy ensemble. It's like a balanced random forest, but more general. It can work with any of the base classifier. You don't need to have a random forest, rather you can have any other like SVM or logistic regression, any of these things you can have the same. Now there is another algorithm called Boost algorithm. So it's basically under random undersampling plus AdaBoost. And here what we do is you combine these two techniques. So you undersample the majority class based on sample weights and sample weights from AdaBoost itself, and then you train the weak learner on the balanced data set, and then you update the weights basically, and then misclassified samples get higher weight, and then you repeat. And I hope you remember the ensemble methods, random forest, the let's say bootstrapping, and then let's say boosting, and that this was the balanced random forest and easy ensemble were the answers from the like a random forest side of view, like bootstrapping side of view or bagging side of view. This one is more from a boosting side of view. Yes. And generally, what we do is basically ensemble techniques will eventually create larger diversity by looking at the majority samples in parts. But then each model actually sees individual, but each model will see only balanced data set. But as a whole, the entire bigger ensemble model sees the entire data set. Yes, fine. Now, what we have is this a little bit more advanced, let's say. Uh, like a class balanced loss, these are more into like Little bit more, maybe this might work only specifically to few domains, but these are still very good methods to understand and learn from. So what we do is the same principle, but the idea is basically not every sample is equally informative, right? The 100th sample will typically add less information than the first sample, and this is the law of diminishing returns, right? And then what we have is effective, we calculate something called effective number of samples, that is given by 1 minus beta per n by 1 minus beta. And beta basically will control your diminishing rate. Yes. And if it is closer to 1, then we have very strong diminishing results. And as we increase the n, En grows basically sublinearly. Yeah. And we reweight the classes again by 1 over e to the power n, En, instead of 1 by n. And it is more principled than, let's say, inverse frequency. We studied something similar earlier also, but that we did it in the data part. This is done more in the loss part. And to get even more things, we can combine it with focal loss, and uh, a class balanced focal loss will be really, really good. Yes. Uh, then another one was decoupling. So now some of the observations before we start is basically representation learning and classifier learning have different requirements. Representation learning is more into like understanding what the data is, let's say. Can we understand from the data itself without looking at the task? Classifier learning has a particular task already in it. And so again, just repeating, so good representation will be learned from all the data. Good classifier needs, let's say, balanced classes, and we just need to find out, right, the distribution, the decision boundary. Now, what do we do in decoupling per se? We separate these two. So first we do a representation learning, that we understand what the data is, right? Uh, so we train the full network with normal sampling, which it understands, okay, this is how data set looks like, right? These are the features, these are generally the relationship between the features, but the labels can be different way. That's a different story. Then what we do is we freeze it. Part of it we freeze. Basically, the encoder, let's say, is what is getting freezed, and only the classifier will get trained with a class balance sampling. Right. So that means if I have been given 90 and 10, what I will do is initially I will learn from all of the 100, right? But then of course we understand it does not understand, how do I say, the minority and majority distinction very well, but it at least understands the data itself. Once that is done, once I have understood the data, I will freeze my encoder. Encoder is what freezes, encoder is what basically converts the real world data into something, into a transformed space where uh, other operations happen. But we can freeze that and then only fine tune the classifier with a class balance sampling, right? So now why does this work basically? So of course, like the encoder will learn general features from all the data, and the classifier learns proper decision boundaries given the balanced data. So it's very simple but very nice. So decoupling. And then the next one is basically balance softmax. It's a standard softmax that basically will ignore the class priors, and it adds basically, if you see, the log pi c is getting added and the log pi j. Okay, the both c and j are from different classes, let's say, and j is basically across all, but c is for the class that we're looking at, and this will adjust for the natural class imbalance that is there in the data distribution. Yes. So I hope you have a little bit flow. So I'll just repeat it for a bit. So initially we started with the problem itself, the class imbalance problem. We looked at what is the impact it can have. Then we looked at what are the metrics that we should look at. Accuracy is not working, so F1 score, MCC, then ROC AUC, precision recall curve, Then we looked at how can we manage class imbalance. One of the methods will be data level methods. The other one will be, let's say, algorithm level methods. And we looked at a variance of like smart techniques to attack basically from data point. Then from algorithm, we looked at cost sensitive learning. How do we update the loss functions to help understand or give more priority to the minority classes? Then how to do adaptive, basically giving weight the focal loss does. Then we have ensemble methods, which each particular individual model will see balanced, but overall model will see everything. And then there is Rust Boost, which combines both of them. Then there is class imbalance loss. Then we looked at decoupling, very nice, where we start learning about the dataset first and then understand about class balancing. Now, the next is a little bit more advanced, but I will keep this in the slides for you to go through, but I will stop the class now, but I will keep this in slide, but at least we have covered the major parts. And it does not just end here, of course, like there are many more techniques as such I have noted down in the slides, but I hope you will go through if you see a problem. And there are few questions, though I will just answer as an FAQ, like which method is the best. Sorry, like it's typically will depend on how much is the imbalance, what is the data set size, what are the domain constraints, and all this stuff, right? What is the computational budget you have? And typically, SMOT you use if the small data set, just use SMOT. Can we not just collect more minority class data? That would be one question. Like answer is sure. If there is chances, sure. But like for example, you want to understand at what point, let's say accidents happen, right? But accidents compared to, let's say, regular traffic is very low. So just because you want, it does not happen, and also you would not want to happen. And then what about multi-class imbalance? Whatever we have discussed before, we discussed about two binary classes, but all of them are binary class. But you can extend it to like more than two classes as well. It's just that instead of having class weight only for two, you will extend it for multiple. Yes, confusion matrix will look bigger and so on. Now, how do we know that if your thing is working or not? Of course, like the metrics that we studied, so F1 score and MCC. Yeah. Okay, and it has to be also like you can do some statistical tests to understand if your results that you have got are statistically significant or not. Yes. Okay, with this, I will stop on class imbalance. I hope this is a good topic for you to revise in case things are not working particularly on the fine. Okay, I will stop now. If there are any questions, I'll be there. Otherwise, yeah, we'll meet on Wednesday.
Yeah, actually, I'll show an example from the materials domain about class imbalance and
Yes, yes,
uh, our calculations, how we took care of that. One of the methods that you discussed, not very sophisticated, but it will
right.
give them an idea how results change as one uh,
Correct.
tries to take care of class imbalance. But most often, the class imbalance is not as dramatic in the materials domain as it is in, say,
Okay.
medical test
Yes,
or fraud detection.
true,
So
true.
that way we are better placed.
Now, I was saying, like, for example, if you wanted to do that magnet thing, let's say rare earth magnet, but those are very tiny set of alloys, let's say, that are present. Maybe, I don't know.
No, even a
Uh,
very even a simpler example they can easily appreciate is you want to classify materials as whether it's a ferromagnet or an antiferromagnet. And if
yes,
you look at any data set, there are many more ferromagnets than antiferromagnets.
I see. Yes.
So how
But,
to deal with such situations?
yeah. So, yeah, basically, we were trying to cover the things where failures can happen, but there are already people who have thought about it and techniques already exist so that you don't feel disappointed. Okay, no, ML does not work. Yes. Probably there are some other things that we should look at.
Yes.
Yes. Okay. Yes. Fine. Fine. I'll end the class maybe Wednesday. Yeah.
Yeah, we'll meet on Wednesday.